Okay, Chemistry 3112, this is experiment 17.1a, the Microscale Wittig Synthesis of trans-9,2-phenylethanol anthracene. The Wittig reaction is what we call a name reaction in organic chemistry, meaning it's named after a scientist who developed it. It's named after Georg Karl Wittig, and he won the Nobel Prize for this reaction in 1979. And a theme that you find in organic chemistry is a lot of Nobel Prizes have been won by organic chemists who develop new ways to make carbon-carbon bonds. The Wittig reaction is very important in organic chemistry because, like a Grignard reaction, the carbon skeleton of a molecule is modified, meaning we're going to form new carbon-carbon bonds. In the Wittig reaction, a ketone or aldehyde is converted into an alkene with the formation of a new carbon-carbon double bond. And I have a couple of examples here. The one here on the left-hand side shows a ketone reacting with this reagent here. This is called a Wittig reagent, and we end up producing an alkene. In the second one, we see something similar. Here we have a ketone that's inside a ring. This is cyclohexanone. Again, we treat it with that Wittig reagent, which we're going to talk about more, and we produce a carbon-carbon double bond or an alkene. A little more information about that Wittig reagent. The Wittig reagent is a phosphorus ylide in which the carbon atom acts as a nucleophile. And you can see that in this structure right here that we call the ylide, this is the ylide, that we have a negative charge on our carbon. And so it's easy to see why that carbon would be nucleophilic. Now you also see that the ylide has a resonance contributor shown here, and we call this the ylene. And in the ylene, we show a pi bond between the carbon and the phosphorus. And the greater contributor of these two resonance structures is in fact the ylide. And the reason why is because of the inefficient 2p and 3p orbital overlap in the formation of this pi bond here, because carbon is from the second period and phosphorus is from the third period. And so our ylide overall is a neutral compound that contains a negatively charged carbon adjacent to a positively charged phosphorus. Oftentimes, Wittig reagents are simply synthesized in the lab, and they're synthesized via a two-step process from the corresponding alkyl halide. So we start out with our alkyl halide, and we treat that with triphenylphosphine, followed by treatment with N-butyllithium. And so in the first step, the triphenylphosphine acts as a nucleophile and displaces the halogen in an SN2 reaction. And since this first step is an SN2 substitution, primary halides or methyl halides are more easily made into Wittig reagents than secondary halides. Once the halogen has been displaced and we have the halide, we form a phosphonium salt. And the phosphonium salt is then treated with butyllithium, which is shown here. And butyllithium deprotonates the phosphonium salt to produce the Wittig reagent. Both the ylide and the ylene are shown here. Let's take a look at the Wittig reaction mechanism. There are actually a couple of proposed mechanisms for the Wittig reaction. The first one is shown right here, where we have a 2+2 cycloaddition reaction occurring between the carbonyl of the aldehyde or a ketone and the ylide. So once the 2+2 cycloaddition occurs, we end up with this four-membered ring that has both a phosphorus and an oxygen in it, and that four-membered ring is called an oxaphosphetane. The oxaphosphetane can then undergo a decomposition to produce triphenylphosphine oxide, shown here, and the alkene. The formation of this especially stable triphenylphosphine oxide byproduct drives the equilibrium to favor the formation of the desired alkene. The acronym that we use for triphenylphosphine oxide is TPPO. A second proposed two-step mechanism is shown here. In this mechanism, there's a formation of an intermediate known as a betaine. Now, I've heard it called a betaine or a betaine. Either one is fine with me. But what happens is that in the first step, we get a nucleophilic attack by the ylide onto the carbonyl compound. Then we form our betaine intermediate, which closes up to give you the oxaphosphetane, which can then undergo a fragmentation to produce triphenylphosphine oxide and our desired alkene. The ylide formed in our experiment will be formed from benzyl triphenylphosphonium chloride. And instead of treating this benzyl triphenylphosphonium chloride with N-butylithium, we're going to treat it with sodium hydroxide. And the reason why we can use sodium hydroxide as a base is because the ylide that's formed is resonance stabilized. You should be able to draw all the resonance contributors starting with a couple of arrows like that. The acronym that we use for benzyl triphenylphosphonium chloride is BTPPCl. Let's talk about the solvents used in this experiment for a minute. While most reactions are conducted under homogeneous conditions where everything is dissolved and can move around freely so that the reactants can collide, it's not going to be the case in this experiment. The reason why is because sodium hydroxide is strongly hydrophilic, it's ionic. The phosphonium salt, benzyl triphenylphosphonium chloride, is also ionic. And when we have ionic compounds, we think of them as being soluble in water. On the other hand, the aldehyde is strongly hydrophobic, so it won't be soluble in water, and the alkene is also hydrophobic. Now, instead of having just a single solvent then, we're going to have to use a solvent system that includes both water and dichloromethane. The first thing you're probably thinking is, well, water and dichloromethane aren't miscible, so we're going to end up with two separate layers. The sodium hydroxide and the phosphonium salt, benzyl triphenylphosphonium chloride, are going to be in the aqueous phase. The aldehyde and the alkene product are going to be in the organic phase. Well, the ylide has no overall charge, and thus it can switch back and forth between both phases, both the aqueous and the organic phase. So the reaction is actually occurring at the interface of the two solvents. This is called a phase transfer reaction. Phase transfer can only take place at the interface between both the aqueous and organic phases. In order to maximize the contact between the two phases, it's really important that the mixture be well stirred to provide lots of tiny droplets so that the organic and aqueous solvents can interact. The take-home message from this slide is that you're going to have to stir your reaction mixture very well. We've looked at the mechanism of the Wittig reaction so far. Let's take a look at the proposed mechanism for our experiment. First, we're going to take the benzyl triphenylphosphonium chloride and deprotonate it with sodium hydroxide to form our ylide. The ylide is going to act as a nucleophile and attack the aldehyde on 9-anthraldehyde. We end up with our betaine intermediate, shown right here, which closes up to give us the oxaphosphetane, which undergoes a fragmentation to produce our desired product and triphenylphosphine oxide. You should be able to draw all of the curved arrows for this reaction mechanism. Here's the overall reaction of our experiment. We're taking our benzyl triphenylphosphonium chloride. We're combining it with the aldehyde, 9-anthraldehyde, in aqueous sodium hydroxide and methylene chloride. We're going to stir it really well, and we end up with our product, which is the trans product. Rather than make the phosphonium salt, and I have the synthesis outlined here in blue, which is just the combination of benzyl chloride and triphenylphosphine. The benzyl triphenylphosphonium chloride is purchased, and so we have that readily available to us as a solid in the lab. If you look at the procedures in our lab manual, it says that you can do the reaction in either a dry 5 milliliter conical vial with a spin vane or a 10 milliliter Erlenmeyer flask with a stir bar. We are only going to be doing the reaction in the 5 ml conical vial found in your lab kit, and of course we're going to be using a spin vane. You always want to check your conical vial for any chips or cracks and make sure you're using a septum that has no holes. Also be sure that your spin vane is pointing in the right direction. The order of addition doesn't matter, whether you add the 9-anthraldehyde or the benzyl triphenylphosphonium chloride first, and that should cut down on wait times. Here's a picture that I took in a previous semester of a student's reaction. You can see the 5 ml conical vial here. This is the 5 ml conical vial. You can also see that it's held in the heating block so that the conical vial won't fall over. You want to spin the spin vane, which is in here. You want to spin it at the fastest possible rate. So you're going to want to adjust the spin rate so that it's fast enough that you can get the maximum amount of stirring, but you don't want to do it too fast because then it will cease to stir. Something that students find tricky sometimes is performing extractions and drying organic phases. You're going to transfer your reaction mixture to a small Erlenmeyer flask in order to dry it with sodium sulfate. Be sure to keep all chemicals inside the fume hood, as extraction can be a little bit messy from time to time. Then you're going to transfer your dried organic phase for evaporation in a beaker. This is one of those rare times when you're going to get to heat up an organic solvent in a beaker on a hot plate. Make sure you have a boiling stick in the beaker when you place it on the hot plate. Also, if you're unsure as to whether your organic phase is dry or not after you've added your sodium sulfate, you can speak to your instructor about it, and he or she should be able to provide some guidance. This is just a shot of a student's fume hood while they're working on getting ready to dry the organic phase. You can see that they kept the 5 milliliter conical vial in the heating block in order to have it stabilized, and they've removed the organic phase, and so the dichloromethane, or the organic phase, is in this Erlenmeyer flask. Now they're ready to start drying it with sodium sulfate. In order to get the correct mass for your product, it's important that you tare your small beaker before you begin the evaporation. Since the boiling point of dichloromethane is around 39.6 degrees, you're going to want to set your hot plate to around 50 or 60 degrees Celsius in order to get it to evaporate efficiently. Also, use a boiling stick and watch for splatter. If there's any splattering that occurs, be sure to turn down the temperature to avoid that. What you're going to see is that when the dichloromethane is almost all gone, you're going to get down to sort of a syrupy consistency. Then you want to take your boiling stick and you want to kind of move that syrup around while the last little bits of dichloromethane are evaporating out of there. And you're going to see it go from a syrup, kind of a syrupy consistency, to a powder very quickly. Try to use your boiling stick to remove any of the clumps in the powder. That powder is your crude product. Here's a picture that shows the evaporation of the dichloromethane from the organic phase. You can see the boiling stick is in there. Once your dichloromethane has all been evaporated off and you get the powder, you're going to want to scrape that into a tared vial, record the mass, take a melting point and a TLC. Because of limited time, we're not going to be doing the recrystallization. If you feel that you have enough time to do the recrystallization, approach your lab instructor and she or he should be able to help you get that started. As always, you want to make sure that you're well prepared before stepping into the lab. Please be sure to read all of the following. First, you want to start out by reading Experiment 17.1a. That's a typo. It should say Experiment 17.1a. And Part A is the experiment you're doing. That's where your procedure is going to come from. It would also be wise to read Chapter 19 in Klein, which is the aldehydes and ketones chapter, and has the parts that pertain to the Wittig reaction in it. As far as techniques go, be sure to look over Technique C, melting point, Technique F, recrystallization, and Technique K, TLC. For your PreLab, remember that these pages must be scanned and submitted with your final report. You're going to want to have your standard header with the full name, date, and title of experiment on the first page. You can abbreviate the title on the remaining pages. Then you have a purpose. The kind of questions you want to ask yourself when developing your purpose are: what are you synthesizing? What are you putting together in order to make the product? How are you purifying it, if you even are? And how are you isolating and characterizing the material? In the table of reagents, be sure to include the name, structure, molecular weight, melting, or boiling points as needed, the concentrations of aqueous acids. Remember the physical properties that are needed for the experiment, and be sure to include your source. You need a safety table with the specific hazards of each chemical listed from the chemical list, a balanced chemical reaction, a limiting reagent and theoretical yield calculation, and your procedures. Be sure to incorporate any changes, and also be sure that your procedure is written in the proper 2-column format in your lab notebook. Product characterization is pretty quick. You're going to mass the product, and you're going to take a melting point. You're going to take a TLC. On the TLC, be sure to spot the starting aldehyde, the triphenylphosphine oxide, which is the side product from the reaction, an authentic sample of the product, the crude product, and you're not going to be making the recrystallized product, so we'll scratch that one off. You're going to develop your TLC in pure dichloromethane, And then in the data sheet, you're going to find a spectrum of an IR spectrum of the recrystallized product and an NMR spectrum of the recrystallized product. A few helpful hints to make things go a little bit smoother. Remember, the amounts in the textbook are approximate. You just need to be near the value. You don't have to get exact values, and that way you won't hold up the line too much. Remember to use your 5 ml conical vial. Remember to have a septum that doesn't have any holes. If all of your septa have holes, talk to your instructor. She or he can provide you with one that doesn't have any holes. Dry your organic phase in an Erlenmeyer flask, not a conical vial, and be sure to tare the beaker before you start evaporating the organic phase. Use a boiling stick, do not use a boiling chip, and while you're evaporating, you're going to see lots of bubbles. You're going to know that you're done when the bubbling stops and the liquid turns thick or syrupy. Again, stir that gooey or syrupy organic phase with your boiling stick until it dries and becomes solid. This can be a tough lab to complete on time, so make sure that you are completely organized.